Welcome back, Shaler area. This is note video number 12 in the physics unit. And in this note video, we are going to start specifically talking about our simple machines. This one's going to focus on the inclined plane and two other machines that are really just kind of like inclined planes in disguise. They're all essentially the same simple machine, just used in three different ways. So you probably call inclined planes ramps. An incline means that something is tilted, and from math, a plane, remember, is like a flat surface. So this is a tilted flat surface. Well, how would a tilted flat surface be a machine? Well, remember, machines are things that make a job easier by doing one of two things. They either reduce the amount of force that is needed to move an object, and if you're going to reduce the force, then you have to increase the distance, or you decrease the distance, but that comes at a cost of increasing the force. Or remember, there is a third thing, and that's if you're changing the direction. Well, inclined planes happen to do a couple of those things. So one, they let you exert the force over a much longer distance. So by nature of machines, that's going to mean that it causes you to exert less force to do so. So to use an actual example, if I had a box, and with the magic of technology, I can draw a box. If I had a box and I wanted to lift that box straight up in the air, well, I could do that. That would take a certain amount of force. But if I use a ramp and I push that box up a ramp, it actually takes less force to do so. The question is why? Why does it take less force to do so? Well, before we get to that question, let's solve for mechanical advantage. You're going to see this a lot. Mechanical advantage is the thing that we are going to look at with every single one of these simple machines, because this is what makes a simple machine give you superpowers. To calculate the mechanical advantage of an inclined plane, you take two of the lengths of the inclined plane and divide them. Mechanical advantage in this way is really just a ratio. You're just comparing the lengths of two sides, and the ratio that you get when you compare those lengths is the amount of times that this machine magnifies your force. So in an inclined plane, it is the length of the incline, so the hypotenuse, or the sloped part, and this is something that people confuse all the time. So if you need to make little notes or write little things, this is the sloped or the slanted hypotenuse line of the triangle. You take that length and you divide it by the height. So to help you remember a little bit, I like to say that it's a love over hate kind of relationship. So if you can remember that it's length of incline, the height of the incline, it's love over hate. So here we have a ramp. We have a ramp. Now all of these ramps that we're going to be looking at have a nice perfect 90-degree angle on them, so we don't have to worry about anything like that. So all of these ramp simple machines, inclined planes, are all 90-degree triangles. You're going to get more complicated than that. You can do that in physics at high school. So which two sides do we divide together? Well, this is the incline. This is the height. So it would be 13 meters divided by 5 meters. Oh, Mr. Reagle, you should have meters over there. But remember, meters over meters, they would cancel out because mechanical advantage doesn't have any units. 13 divided by 5, 2.6. It's just a multiplier. So this ramp would multiply your force 2.6 times. It would literally make you 2.5 times more powerful, or at least more forceful. Here we have an inclined plane that is a little bit shorter and a little bit steeper. It's 3 meters tall, 5 meters on the incline, so 5 divided by 3 is 1.7. So notice when we made the ramp higher and shorter, it made the ratio go down. So the longer and flatter the ramp, the higher the mechanical advantage, the more it helps you do your job. Well, here's one that's pretty long. 40 meters across the bottom, 41 meters across the slope, 9 meters high. 41 meters is really long. If you think about it, that in realistic purposes, that's like half the length of a football field to go 9 meters tall. So what would the mechanical advantage of this be? Well, 41 divided by 9. This ramp would have a mechanical advantage of 4.6. So that means that if you had to push something, if you had to lift something 9 meters into the air, all right, however you're going to maybe climb a ladder, hook up a ladder, throw a box on your shoulder, climb the ladder, lift it 9 meters in the air, remember that's like 30 feet, that'd be tough. That would require a certain amount of force. Well, it would require 4.6 times less force if you put that box on this long ramp and slid it to that same height. Now, when we are talking about all of this, remember we are pretending that we are not losing any kind of energy to friction when we're sliding this up. So there is a law of diminishing returns. Yes, the longer you make the ramp, in real life, the longer you make the ramp, the easier it is to move the things around, but the longer you have to slide something, the more you're going to lose stuff to friction. So we're just kind of like pretend friction doesn't exist when we do all of these things. Like I said, if you were learning rocket science in college, yes, you'd have to take all of those frictional coefficients into account, but we are not doing that here. But wait a minute. Something's weird. If you remember from a previous note video, we looked at this. We looked at mechanical advantage. The global equation for mechanical advantage is always output force divided by input force. So it's the amount of force that you get out of the machine divided by the amount of force that you put into the machine. So if something has a mechanical advantage of 2, and I put 2 units of force in, I would get 4 units of force out. If I put 5 units of force in, I would get 10 units of force out if it was a mechanical advantage of 2. So how does that correspond with the inclined plane? If the mechanical advantage is output force divided by input force, why is the equation to calculate that for an inclined plane the length of the ramp divided by the length of the height, or the height of the ramp? I know when I started learning about simple machines, and in science in general, you always look for patterns. You always look for little things that you see that are relationships that help you remember them. That's what we do when we study. And it's very easy to go down a wrong direction road here with simple machines, because everything we're gonna look at is gonna seem a little wrong. It's gonna seem a little backwards until you get explained what's actually going on. So I'm going to take a minute and I'm going to explain exactly how an inclined plane works. Now, this is not something that you are going to be tested on. This is actually geared more towards geometry level math. I'm going to try to do it to explain to you why inclined planes work, to kind of really deepen your understanding and make those connections. But if you don't understand what I'm about to show you, don't worry about it. It's not something that you're going to need to be tested on. So let's break this down. If mechanical advantage is the output force divided by the input force, then the question here is, why is that the equivalent of the length of the slant divided by the height of the ramp? Because if you really think about this, if you're looking for connections, you would think, I am pushing the box up the slope of the ramp. So that's my input. That's what I'm doing. I'm actually doing this when I use the machine. And what do I get out of the machine? I get a box up here. I get a box that's the height of the ramp. So if you were just sitting down and trying to make these connections, this would seem upside down. It would seem like our fraction was actually input over output, when it needs to be output over input. Well, it's really not the case. I know it looks like that's what we're doing, but it's not. For one really, really, really important reason that I would hope that if I let you stare at this long enough, you would pick up on. Well, this is force, and force, and force is very different from distance. We've learned about all of these different measurements. You can't just take one measurement and swap it in for another one. Physics does not work that way. So we can't look at the distance and say, oh, this is it looks like this is where we're putting the force in, so that means, or it looks like this is where we're sliding the object for the distance in, so that should be the same thing as the force in. That's not the way it works. But let's take a look at some geometry so you can see how it is that we are able to calculate the mechanical advantage, which is force out over force in, using lengths. Because there is a relationship between the two. One does not equal the other, but we can use one to represent the other. But in order for you to see how this works, we need to look at some geometry. All right, so an inclined plane, how does this really work if we break it down? How does this just like unmoving triangular shape structure actually help us do stuff? Well, an inclined plane allows us to lift an object to a new height without having to use the full force of our muscles to match the full force of the weight of the object. It literally like makes the object lighter to us. It makes it so we can use our feeble muscles to lift something that a human shouldn't be able to lift to a certain height. Well, when we lift something, we are picking up its weight, its full force of its weight. Well, what would the weight of this box be? How would we determine the weight of the box? Well, what's weight? Weight is a force. How do we calculate force? Hopefully in all of your heads you just thought F. F is force. What's F equal? F equals ma, that most common formula that we talked about that you use in science. So if F equals ma, the force of gravity is pulling straight down. And this is the weight of the box. So if force is equal to mass times acceleration, and in this case the acceleration of gravity, this vector, remember when we talk about arrows, when we talk about speeds or forces, these are called vectors, just like in the Minions movie. It is a force with a direction. So the force of the weight is mass times the acceleration of gravity. So if we were just lifting the box straight up, this arrow, this vector represents the amount of force that we would have to use. But if you remember when we talked about projectile problems, when we did projectile problems, I said you have to solve the motion of the projectile in two steps. You have to separate the horizontal motion from the vertical motion because they're not connected to each other. That's something a little bit similar to what we have to do here. This tool actually splits the weight of the object. It splits the pull of gravity in two different directions. It splits it perpendicular to the ramp, so at a perfect 90-degree angle to the ramp, and in the direction parallel to the ramp. It actually divides the pull of gravity. And we're going to label these the weight of the box perpendicular and the weight of the box parallel. And the arrows are actually drawn to scale with how much of that force there is. So it divides this whole arrow into two other arrows. Now if we would take these arrows, if it was actually drawn perfectly to scale, and we would take these two arrows and put them end to end, measure their lengths, it would exactly equal this length. That's how vectors work. When you get into physics at the high school, everything is drawn right to scale, and you can actually see how all of this stuff starts to work together. So anyway, we have this weight of the object based on gravity split now into two different parts. The part that is perpendicular to the ramp and the part that is parallel to the ramp. Well, we've learned about Newton's third law. Newton's third law is that of equal and opposite forces. So remember how you jump, you push into the ground, and the ground pushes back on you. So if there is a force that's pulling down on that box, but it's pulling down at the angle that the surface is where all that pressure is being applied to this tool, the tool, the inclined plane, pushes back up with the same amount of force that gravity is pulling down with at the angle of the inclined plane. So if this is the weight perpendicular, if this is how much force is being pushed straight down onto the ramp, or pulled, I should say, straight down onto the ramp, that's how much force the ramp pushes back up. So these two arrows are equal to each other. They're just at 180-degree angles. They're working opposites to each other, but it's exactly the same amount of force. That means that the tool is actually helping you lift the object by balancing this amount of force. That only leaves this amount of force that you need to push to move the object, because it's actually pushing with this amount. So it literally divides the pull of gravity into these two vectors and then supplies one of the vectors for you. It looks like it's not doing anything, but because of Newton's third law, it is pushing up with the same amount of force that the box is being pulled down with against gravity. So that right there, you can see where that ratio would come from. All right, this is the hole out. This is the amount you have to put in. So the mechanical advantage is the ratio between these two arrows, but we'll get to that in a minute. Do you remember the snowman problem? In the snowman problem, if you don't remember the snowman problem, it was one of the first ones that we looked at forces. It was one of the first times we used the Pythagorean theorem in class. In that problem, I said that there was a winter storm and it blew your Frosty the Snowman winter decoration up into a tree, and then you had to pull it down out of the tree, and you had two people, and you were pulling at 45-degree angles on the ropes, and we drew the vectors, and we moved the arrows around, and we made another triangle, and we used Pythagorean's theorem to solve for what the straight up and down line would be, which would be the combined force of the two ropes. But the whole point of that is that I wanted to show you that you could move these vectors around. You could rearrange them in a way that makes the problem easier to solve. Well, watch what happens if we take the parallel weight arrow and we move it a little lower. So I didn't change the angle, I didn't change the length of it, I just moved it into a different place. And what did we make? We made another triangle. And if you use the rules of geometry, specifically the alternate interior angle rule, you could write a proof that would say that this angle of this right triangle, so we have a 90-degree angle, and we have this angle here, it's usually called theta, that is the exact angle of this angle. And this is the 90-degree other part of it. So if this angle is the same, and this angle is 90 degrees, and this angle is the same, and this angle is 90 degrees, that means that the third angle must be identical as well. That makes these two triangles have a very special relationship with each other. They are similar triangles, which means the ratios of their sides is going to be identical because all of their angles are the same. So if this is the force of the weight, if this is the output, in other words, when we use this tool, doesn't matter how much force that we are putting into it, if we are lifting it up in the air, this is what we're getting out. We're getting out the pull of gravity, the weight of the object. But all we're putting in is the parallel part. That's all we have to apply because the machine is adding this part. Well, if these angles, if these force vectors, remember back to forces, have the same ratio as the sides of the triangle, we don't have to do all of the geometry and calculate the forces because we can just use the lengths of the triangle. They match up. So that means this hypotenuse represents, remember, when we measure the length of the hypotenuse, we're not measuring force, we're measuring length, but that length represents, on the force triangle, the length that is the work out, or I'm sorry, the force out. And the height of the triangle, the height of our ramp, corresponds to this little bit of parallel force that we have to apply as our input. So when we are doing hypotenuse over height, or the length of the hypotenuse, the love, over the height of the height, we are actually having the same exact ratio that is the force out and the force in, which is our mechanical advantage. Just let that sink in for a second. That is how the machine actually works. The machine works by providing the other side of this pull, by splitting gravity in pieces and you only having to apply one part of that piece or one of those pieces to actually lift the object up in the air. That's how a ramp makes you superhuman. Like I said, you don't have to understand any of that. You're not going to have to answer any questions on any of that. You're not going to have to redraw any of that. That is just there to give you a deeper understanding of how this tool works, rather than just memorizing what the tools do. There's a reason that they do what they do. That's where the actual physical science comes in. It helps your understanding. All right, so the next tool is a wedge. First one's an inclined plane. This one's a wedge. And a wedge you can think of as two inclined planes stuck together. If you've ever used a wedge for anything, the most common wedges that I use, I think, are probably to split wood. Wedges work a very similar way. They lessen the input force. They make it so that you don't have to apply as much force, but they do that by increasing the distance, and they also help by changing the direction. The biggest difference between a wedge and an inclined plane is that on an inclined plane, the ramp sits still and you push the object up the ramp. With a wedge, the object's, well, I guess it kind of moves in the end, but the object is not what you are pushing on. You're actually pushing on the ramp, and you're pushing the ramp through the object. So what are some things that are some real-life examples of wedges? Teeth. You know, when you bite through your food, you're pushing this ramp. If you think about it, it's pointy at the end and it's wider at the top, so that's a tiny little wedge. You have a whole bunch of them, and you have different angles and different points. And this is an amazing evolutionary technology. So if you think about it, the way a wedge works is it requires less force to do something. It requires less force to bite through objects. It requires less force to chew up your food so you can get more nutrients out of them. You might not be able to chew through certain foods, but if it wasn't for the wedges of your teeth, you don't have to have huge, powerful facial jaw muscles in order to actually be able to chew up your food because of the wedges of your teeth. Now, if you think of some other animals, how sharp their teeth are and how sharp their claws are, these are ways these are adaptations, these are like evolutionary components that have happened so that you don't have to have big, strong, powerful muscles to accomplish a lot of force. Now, if you have these tools and you have big, powerful muscles, wow, what you can accomplish is off the charts. Well, we don't have razor-sharp talons like hawks and eagles and things do, and owls. So we, as humans, have made tools, and that's really what these simple machines are. These are all tools. Things like knives. We don't have, we have fingernails, and yeah, they can be helpful, but not nearly as helpful as a knife if you're trying to actually, use your force to do something. An axe can split wood. You can grab that log and pull on it with your fingernails all day long, or your teeth for that matter, and it's not going to split in half. You use an axe, you split it right down the middle. Wedges are also used in things like scissors. These are two layers, so if you could actually look down in the middle of this, there is a wedge here that causes these two things to piece together, but specifically also to pull them apart. It's really hard once these things are zipped together. You need the power of a wedge to break them back again. So the mechanical advantage of the wedge is the length of the wedge divided by the thickness at its widest point. You might want to put little stars next to these because I don't give you these formulas on a quiz. So you're going to have to remember how to calculate the mechanical advantage of each of the tools. So this might be something that you want to put down. This is why I recommend flashcards for simple machines, because remembering how to calculate these mechanical advantages, it's a memorizing process. If you understand how they work, that helps you not necessarily need to just memorize it, but memorizing is a really important part of learning. It is something you need to learn how to do, and flashcards really work nicely with that. So here's a problem. Let's say I'm going to use this wedge to split this log. I find wedges and sledgehammers to be far more effective at splitting logs than axes. You can really pinpoint where you're going a little bit better. You can create a lot more force. So how does this work? Well, we have a 20 centimeter long wedge, so the distance from here to here is 20 centimeters. All right, 8 centimeters thick. That's this distance here at the widest point. That is not if I could spin it around and look and see, you know, how wide it is from like looking from this viewpoint over here. We're talking about the actual like splitting surface, not the surface that's sliding along the log, not like that hypotenuse ramp. We're talking about this side here. How wide is it versus how long it is? Well, if it's 20 centimeters long, 8 centimeters wide, that means this wedge has a mechanical advantage of 2.5. It multiplies whatever force I hit the top of that wedge with 2.5 times. And not only that, but it also changes the direction. I'm hitting down, and it's causing the direction to go outward from both sides. It's really what makes it possible for you to split wood. So let's put all of this all together. We're going to backtrack. We're going to bring in things like speed and velocity and acceleration and efficiency, which we learned about in a recent note video. So let's say that this wedge that has a mechanical advantage of 2.5, which means it's going to multiply our force 2.5 times, is hit with a sledgehammer. The sledgehammer has a mass of 4 kilograms, roughly 9-pound sledge, and we can swing it with an acceleration of 4.5 meters per second squared, which would be the equivalent of 10 miles per hour every second. If the system has an efficiency of 80%, which means only 80% of the force actually makes it through, everything else is lost to friction, how much force is being applied to the log by the wedge, causing it to split apart? Well, where do we start? F equals ma is always a great place to start, especially since we need to find force. Anytime you're doing any of this stuff, force is what we're looking for, specifically because, hey, look, force is what we're looking for. How much force is being applied? So we need to know how much force is going in before we can figure out how much force is coming out. Well, if force is mass times acceleration, the mass is 4 kilograms, the acceleration is 4.5 meters per second squared. That gives us a force in of 18 newtons, 18 kilogram meters per second squared. So our input force here, 18 newtons. Now this next step, you could do at any point. You could do this at the end. I'm just going to do it now in the middle to get it out of the way, and it's dealing with this efficiency issue. So if only 80% of my input force is actually going to make it out, well, let's just reduce it by 20%. So if our net force is 80% of 18 newtons, our net input force is only going to be 14.4 newtons. That's where the efficiency. So that represents the amount that's lost to friction, to heat, to sparking if the two things are metals. Anything else there that you could think of that would be friction, we discussed that in an earlier note video. Well, if the force out of the machine is equal to the force in times the mechanical advantage, because remember the mechanical advantage is how many times you multiply this, so this times your force multiplier would give you how much force you're getting out of the machine. So now we just plug it in. If our mechanical advantage is 2.5, and we have 14.4 newtons of force going in after we've accounted for the loss due to efficiency, that means the amount of force that is coming out of that wedge is 36 newtons. We have essentially doubled our force. But not only that, we have doubled it and changed its direction. These lines, these arrows aren't quite right because this would be perpendicular to the surface. They'd be kind of down at angles, but still, we've split the direction. So it's kind of like we've crawled inside this log and we've blown it apart from the inside, pulling outward. You could not do this unless you had a tool to make it happen. Now, if we really wanted to get technical, this 36 newtons of force would be divided in the two directions. So it would be 18 newtons one way and 18 newtons the other way, but again, you don't need to worry about any of that stuff until you get to high school. This is pretty cool. So let's take a look at knives and scalpels. I'm sure you're familiar with those things are. They're wedges. So the newest scalpels that are out there, the ones that are like the most extreme in medicine, and if you had like the top of the line possible best cutting tool on the planet, they are made from obsidian. They're not made of metal, they're made of volcanic glass. It's that shiny black rock that you get from lava rock. It's natural glass. Well, the blades of an obsidian scalpel are 3 nanometers. thick. A nanometer is really small. I think it's like 10 to the negative ninth in the scientific notation. So that would be written here. It'd be 0.0000000003 meters. That's really skinny. It's really, really, really skinny. And they're about a centimeter from the blade to the top. So a centimeter long, widest point is 3 nanometers. Let's compare that to a knife that you guys are familiar with using, like a steak knife. Steak knives are usually made of steel, not volcanic glass. They're usually about a millimeter thick, and you know, you can get different length ones, but we'll just say this one is 2 centimeters between the sharp part of the blade and the top of the blade. Well, let's compare the mechanical advantages of these two, essentially the same tools. They're both knives, they're both used for cutting things. Well, the steak knife, remember, it is the length divided by the width at its widest point. So if it's a millimeter in width, 0.001 meters, don't forget you have to make sure that all these units are always the same so they cancel themselves out. Well, the 2 centimeter wide blade with the thickness of 1 millimeter would give us a mechanical advantage of 20. So when you cut your steak, whatever force you are applying to that meat with your muscles is magnified 20 times. This is why you're able to penetrate skin with a knife. You try to stab something with your finger, it doesn't go through their skin. That's what the skin is for. It's to block that. But if you stab somebody with a knife, it's like you stabbing someone with your finger, but times 20. Right? It is magnifying the amount of force, and it's concentrating it on a much smaller surface. Well, how does this work with the scalpel? You usually think of scalpels as being sharper than knives, because that's what we use, for surgeries and for make really, really clean cuts. Oh, I should point out something. This picture, I didn't explain it. Let's back up here. So these are electron microscope pictures. Forgot to explain this. So remember when we looked at electron microscope pictures before, this is zoomed really, 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 really in. These are the most powerful microscopes that we have access to. We get the really, really detailed views. This is a freshly sharpened, brand new steak knife made of steel. Notice all of the little microscopic pits and jagged things and stuff like that. So if you were to cut something with this, all these little bumps and grooves and jags would tear at cell walls as they were going through, and it would cause damage. And when you were cutting something with a scalpel, this is a steak knife, remember, when you're cutting something with a scalpel, you want to cause as little damage to cells as possible, because that's what leads to scarring. This, on the other hand, is an electron microscope picture of one of these scalpels made out of volcanic glass. It is about as smooth as possible. It's actually possible with one of these to cut between cells, to separate skin cells so that you don't actually destroy them, you just peel them apart from each other. Really minimizes scarring. You don't have anything catching and actually destroying any of the tissue. I mean, at some point you do cut through cells, but it's possible, though, to cause minimal damage. So let's zoom back up here. What would our mechanical advantage of this scalpel be? Well, if the scalpel up here, let's see, remember it is 3 nanometers thick, so this huge decimal, it's kind of like an oxymoron, a huge decimal, goes on the bottom. And the width, which is about a centimeter between the edge and back of the blade, goes here. Well, 0.01 meters divided by 0.0000003 meters, 3 million. That's insane. If you had this knife and you put the slightest bit of pressure on it, it would magnify that force 3 million times. That's a very dangerous tool. It's in fact so dangerous that human doctors don't use these scalpels. It's impossible to control your muscles with enough accuracy and prowess to effectively use this scalpel in the way that it needs to be used. These are the kind of scalpels that robotic arms use during assisted surgeries. That's pretty neat. All right, so what about this? Is that shape an inclined plane or a wedge? Well, your first impulse is probably going to say inclined plane. That looks just like the inclined planes that we were using. Well, it's not quite that simple. It depends on how you use it. Remember I said that these tools that we're going to talk about here in the beginning are all kind of the same tool. They're just used in different ways. So if I was using this to slide a box up to a higher height, that would be an inclined plane. But I'm sure all of you have seen this. That's not being used as an inclined plane. That's being used as a wedge. We are pushing the object, pushing the tool under the door and causing the door to kind of separate from the floor. We're putting an upward force on the door by sliding the tool in. That describes how a wedge is used. So just because it's this shape, you won't know if it's an inclined plane or a wedge until you know how the tool is being used. Is something being pushed up the ramp, or is the actual tool being shoved sideways to separate two other things? And I'm not going to go into great amounts of detail, but here's just a little flash. If I went through all of that rigmarole of doing the geometry again with this tool, the difference here is, all right, so if this is being used as a wedge and we are pushing the inclined plane this way to cause the box to go up in the air, rather than pushing on the box to cause the box to go up in the air, what's happening is our force in is still this, because that's what's going parallel to our surface, but our force out is no longer the pull of gravity. Our force out is no longer the full weight of the object. Our force out is actually going perpendicular to the surface of the ramp. So now the ratio, instead of the ratio being the hypotenuse over the height, our ratio is now the length of the wedge, the base of it, divided by the thickness of the wedge. So it's this side of the triangle, or I should say this side of the triangle, it's the same, divided by this side, which is here. So it's this force out, divided by the force in, and they correspond to those lengths. That's the last I'm going to talk about, like why simple machines do what they do. When we get to things like levers, it's going to kind of seem backwards again, and that gets more complicated with the geometry because now you have things that are like pivoting and rotating. When we get to things like pulleys, that's really just a special kind of lever. So there's really only a couple of simple machines. They're just all used in different ways. Really, an inclined plane and a lever. You could argue that those are the only two simple machines that there are. A screw is often defined, and it's how our book defines it, as an inclined plane wrapped around a cylinder. You maybe have never thought about a screw that way, but if you take a look at a screw, that's kind of what it is. And screws work by decreasing the amount of force that's needed by greatly increasing the distance. You can see the pattern here. It's how this inclined plane thing works. It reduces the force by increasing the distance. So real-life examples of screws are, hey, screws. Imagine that. And you can see how it is this spiraled kind of ramp that goes around a cylinder as it goes up. Bolts are the same way. It's how we attach lids to things. This is an auger. We use it to dig holes in the ground, and spiral staircases. Although this one's a little iffy, honestly. Try to avoid comparing inclined planes to staircases. It's kind of a hot issue, and one that physicists argue about a lot. And there's no real good way to explain it. This is the kind of thing that even like the best physicists will just go, just trust me. You know, kind of the way that people say things whenever they're not able to explain why or don't want to take the time to explain why. But if you really dive into how steps work, it doesn't seem like it works the same way as the ramp because you don't have that sloped surface to divide gravity up because every step is flat. And it ends up being more the way that our legs work than it is the fact that it's a staircase. The reason that it takes less force to go up stairs than it would be to climb a ladder, for example, that would be going straight up and down, has more to do with the levers of our legs than it does with the actual slant of the steps. But like I said, that's not something we need to get into. So how do we figure out the mechanical advantage of a screw? This one is the most complicated of all of the simple machines to remember. It does use pi because we're talking about this round cylinder. So anything that's round in science, you pretty much are going to have to use pi when you're calculating it. So it's pi times the diameter of the screw, the diameter of that cylinder, in whatever units you're using, times the number of threads in, again, whatever units you're using. So I could replace this with inches, I could replace this with meters, I could replace this with kilometers if we had a screw that long. But in general, the closer the threads on the screw, the greater the mechanical advantage. And the reason the units don't matter, because, I mean, if you really think about this, if we put numbers in here, it would be, oh, that's still in box, hold on. If we put numbers in here, it would be like pi times, we can just say like 10 centimeters times, and this next thing is a fraction. If it was like 20 threads in 1 centimeter, see how centimeters cancel out because you have one on top and one on the bottom. So it doesn't matter what units are there as long as they are the same unit. So here's a picture of a screw in your notes, and it's got little lines next to it that aren't going to pop up in the PowerPoint. So you're going to need to do a little bit of counting there on your own. But to figure out the mechanical advantage of this screw, well, it would be pi times the diameter of the screw would be this line down here, and I believe it says in your notes that it's 1/2 centimeter. And then there's a vertical line here, and you need to count the threads. So it would be like, like 1, 2, 3, 4, 5. And in the end, you should count to 9. So our mechanical advantage of the screw would be pi, or 3.14, or 22/7, or whatever pi button on your calculator, times 0.5, the diameter, times 9, the number of threads in that same unit. And we would get a mechanical advantage of 14.13, far bigger than the inclined plane mechanical advantages that we were doing, and definitely far bigger than the wedge ones, because there is a lot of extra distance as you go around here. If you could unspool that, it's actually pretty big. We're going to do something like that in an activity in class. All right, that leads us to the end. That's our booby trap. There is 15 questions. Don't forget to take the time to go and do the exit ticket, and hope everybody has a great day.